Assalamu alaikum everyone. So today is the last topic of our course measurement and instrumentation. So up to our last class we have covered the AC emitters, then we have tried to see the DC voltmeters, then we have seen the half wave rectifier, then the full wave rectifier. So up to this much we have covered from the PMMC part. So later on we will try to see some upgradation of the PMMC. So what's actually we are trying to use instead of the PMMC, and there are some certain limitations of the PMMC. So in the PMMC, what you have already seen, that it's only working with the DC voltages, and when we are trying to work with the AC signal we have to implement some bridge circuits. Okay, so there is a half wave rectifier as well as the full wave rectifiers, right? So in the half wave rectifier there are some certain problems, and also there is a problem that is associated with the full wave rectifier. So if we try to see the circuit diagram of the half wave rectifier AC voltmeter, if you try to see, so we have already seen that if this is the AC signal, then we have our RS, then there is a diode, and we have our PMMC coil, that is IM. Then we have another diode, that is D1, and this one is D2. Now the main problem of this half wave rectifier as well with the full wave rectifier is the non-linearity due to these diode mechanisms. So if we try to see the characteristic graph of diode, how the characteristic graph looks like. Right, so these sorts of diode characteristic is there. This is the ID, and particularly this is the VT, the threshold voltage. Okay, so right now if we see that after some certain ranges, this signal, the current that is flowing through the diode, suppose in this particular region, at this particular location, the diode becomes like a shows linear property in this particular region. Okay, but if the current that is drawing by this diode is low, if we try to consider in this particular region, this is a non-linear part. Okay, so in this non-linear region, if we try to operate this voltmeter, then the ultimate goal will be this scale. The scale will not be working in a linear manner. Okay, there will be some non-linearity property. So that's not acceptable, because whenever we are working with the voltmeters, so every time the scale should be in a, the scale increasing or the values should shown in a linear manner. The values should not show in a non-linear manner. Okay, so there should be linearity property should be maintained, but due to this low current that is flowing through this current ID, the current that has been flowing through the diode ID, if it becomes very low, then there is a problem of non-linearity. So how we can reduce this problem, the non-linearity issue? Two ways. The first one, is not so effective, but the second one is very much effective. The first one is nothing but it's the very simple mechanism that from this region, from this low region of current, I want to increase the value of the current. Okay, so for a particular signal, the values are fixed. The current, it's the voltage is fixed for a particular input signal, but the current, I can vary the current. So how we can vary the current? Only a single mechanism, that is, we have to reduce the voltage, reduce the resistance of the voltmeter. So how we can reduce the resistance of this voltmeter? If we just simply connect a shunt resistance like this manner, RSH. So whenever we are reducing the shunt resistance, introducing the shunt resistance, as a result, the resistance of this whole circuitry will become less than the previous version. So the current that will be drawn by the diode D1 will become much more higher, suppose in this area. So from non-linear region you will be able to get the linearity property, but the issue is that definitely whenever we know the sensitivity, right, the sensitivity from the equation, it's about like 0.45. So for Rm plus Rs by V in for the DC. Okay, it's for the DC. So if we see that if we reduce the voltage drop, okay, if we reduce the voltage drop, or sorry, not reduce, if we reduce the resistance, so the formula is like this: 0.45 by IFSD, right? So what you can see, so right now the current that is flowing through this resistance, flowing through the Rm, the Im value will be much more higher than the previous one. So ultimately the effect of this, or the sensitivity of this voltmeter, will reduce. Okay, so that's a major problem, because whenever we are trying to reduce the voltage drop, try to reduce the resistance of the voltmeter. Okay, so it will ultimately reduce the sensitivity. So first step is the RSH, or a shunt resistance, introduced in the voltmeter. Okay, so in our last class we have seen that Im is equals to, we have seen that Im, the full scale deflection current, is also equals to the average current. Why is that? Because when we are connecting these AC voltmeters, so there is a scale and the needle, that is or the pointer, it's rotating. Okay, so if we look into the AC signal pattern, so it's changing. Okay, so if we try to use the AC signal that has a 50 Hertz frequency, okay, so 50 Hertz frequency, so if you do the calculation in about 60 seconds, it's going to change its direction so many times, right? So the needle, that's the pointer that's working, so it has some inertia. Okay, it has some inertia, and due to this inertia it cannot change its positions so frequently. Okay, so it cannot detect, or it cannot move itself so frequently in the upward voltage or downward voltage. So instead of these AC signals, what it do, it shows a smooth transition from the zero value to the selected voltage or the desired voltage range that it will show on the scale. Okay, so the pointer will move in a smooth manner and it will show the average value. Okay, so the pointer, when it is in the physical form we are utilizing in our day-to-day life, so the pointer or the voltmeter will not follow the instantaneous values. Okay, instant values of a sinusoidal signal. So instead of following a sinusoidal signal or instead of following the instant signals, it will try to follow the average signal. Okay, so in the AC voltmeter you will not see any sorts of up and forth deflection. Instead of, you will see the average value. Okay, and that is only possible due to its the pointer's inertia, that is ultimately help you to get a smoother transition. Okay, now to reduce the nonlinearity property, we have introduced a shunt resistance, but it has also some problems that I have already said. So what's the perfect solution? The perfect solution is a different sort of rectifier circuit. I don't know whether you are familiar with it or not. So it's called precision rectifier. Now, what is a precision rectifier and what's the use of this precision rectifier? Precision rectifier is a rectifier where we are using, instead of just a diode, we are utilizing a op-amp with a diode. And the effect of this op-amp and diode is so vast that you will see in a little bit later that it will ultimately help you to work in the linearity property. Why is that? Because the op-amp obviously shows the linearity properties. Okay, so the non-linearity property, the non-linearity issue can be solved with this precision rectifier. Now, if you look into the voltage drop of this diode and the current that is flowing through the diode in this particular portion, that is the lower voltage range than the threshold voltage. Yes, when we are trying to utilize these sorts of devices with this diode rectification model, so you cannot work with a signal where the threshold voltage, where the voltage, your applied voltage, your input voltage is lower than the threshold voltage. So you cannot measure those values. So there is a problem that you cannot find out or you cannot measure all the values. There are some certain limitations because due to this threshold voltage. Now, what's the solution, that how we can measure beyond these threshold voltage levels? That means if my threshold voltage is VT is about 0.7 volt for silicon diodes. So right now my input voltage, suppose it's about like 0.2 sine of omega TV. Okay, so you can definitely see that the peak value, the V in of VP is about 0.2 volts, so which is obviously lower than the threshold voltage. So the diode will not be in the activated mode, or it's not, it will be in the forward biasing condition. So as a result there will be no current flow through the PMMC. But if we use the precision rectifier it will ultimately help you to get these sorts of signals, to work with these low voltage signals. So let us see the diagram of this precision rectifier. Precision rectifier. So in the precision rectifier, what we will do, this is the circuit diagram of precision rectifier for a half wave rectifier. Okay, now some important things that I need to know, that the concept of virtual grounding, then you should know the open loop gain of op-amp is about, that is called the A, that is about 10 to the power 4 to 10 to the power 5, a very large value. Then the output, the V out, it will work in terms of A V1 minus V2. This is the open loop gain. Okay, so in this manner it will try to work. Now I hope all these things are well known to you, that what is the virtual grounding, or what is the virtual point node concept. Okay, so then open loop gain of op-amp is very high. Then how actually the voltages are being generated, so that sorts of things are already familiar with you. So this is nothing but, if you try to see, then it will be like this. So over here this is the V1, then this is the V2, and this is the V0. Okay, so these are the concepts that you need to know. Okay, so first of all, just a very small idea, that is the concept of super diode. Okay, super diode is nothing but op-amp plus diode configuration. This is called the super diode. Why it's called the super diode concept? Because in the diode concept, what we have already known, that there will be some voltage drop due to the threshold voltage. But when we are utilizing this diode with an op-amp, there will be no voltage drop across the diode. Okay, that's the beauty of this precision rectifier that we are utilizing over here. Why there will be no voltage drop in the diode concept, or in this particular configuration? The reason is that suppose over here, if this is V in is greater than 0 volt, so over here this definitely it's my AC signal. So in this particular region or in the positive half cycle, my input signal will be definitely above than the voltage level, right? Okay, so what will happen? So in this particular configuration, suppose this is the V0, this is the V0, and or V0L, this is the V0. Okay, fine. Then what is the V0 value? If this diode is in the conducting mode, so if this diode is in the conducting mode, okay, so if this diode is in the conducting mode, then there will be a voltage drop of 0.7 that you already know, that is like this, 0.7 volt. So if we go to the derivation, so here you can see that is V0 is equals to V0L then plus 0.7. So, and we already know that the equation of V0, okay, the equation of V0 is what? V1 minus V2, that we already know. So over here it will be a V1 minus V2, which is V0L plus 0.7. So if we just try to find out V1 minus V2, it will be what? V0L plus 0.7 divided by A. So right now we already know the open loop gain of A is about 10 to the power 4 to up to 10 to the power 6 or 10 to the power 5. Okay, so depending upon the range of the or the model number of the op-amp. So for the time being, let us consider that A is about 10 to the power 5, which is a very large value. So if we try to provide over here, that is V0L plus 0.7 divided by 10 to the power 5. So this particular arrangement, when the denominator value has a very large value, then the overall thing will be compensated. So this particular configuration or this particular formation will be closer to the 0 volt. As a result, what you will have V1 minus V2 is almost equals to 0 volt. So your V1 will be equals to V2. Okay, now this is my V1 and this is my V2. So whatever you have provided the signal, that will appear at V2. Okay, and V2 is definitely connected with V0L. Okay, so V2 will be also equals to V0L, so that is definitely my V1. So whatever the first half cycle, if we try to see, if this is the first half cycle, for the first half cycle, for this first half cycle, all the voltage or the similar pattern of voltage will appear at the output. Okay, and there will be no voltage drop due to this diode configuration. Okay, now what will happen for the second thing? Okay, or for the negative half cycle. Now again, if we try to see, okay, fine. Now over here, this is the V1 and this is the V2. Okay, so in this particular point, or at the output over here, the V0, what should be the value? So right now V1 is less than 0. Okay, so we have already known that V0 will be the value of is equals to V1 minus V2. Okay, so in this particular configuration, a value is so much large. Okay, a value is so large, and what you will see that the output of this voltage will become a very high negative value, very high negative value. Okay, so if the output of this V0 becomes very high negative value, so we know that in a diode, if you see that this point is connected with the ground, so over here if you just consider that, or this point is directly connected with ground, then there will be 0 volt. Okay, so this 0 volt will appear also over here. Okay, so the 0 volt over here, you are providing 0 volt, and in the P side you are providing a very high negative value. So ultimately this diode will be in the reverse bias condition. Okay, so this diode will not work. Okay, so this diode will not work. So this is the open path. So in this particular configuration, here you can see that what will be the ultimate output? V0 becomes negative over here. So right now in this particular configuration, or in the negative half cycle, what you will see, so from over here the V0 value becomes very negative. Okay, so the diode will be in the reverse bias condition. So right now this is not a closed loop configuration, right now it will be in the open loop configuration. So in this particular configuration, the output, that is the VOL, it will be 0, because the output, it's directly coming from the ground value, and these 0 will be coming over here. Okay, so what you will see that the output of this V0 is very negative. Okay, but you know from the characteristics of the diode, that is it operates in the linear property, right? That is the plus V set and that is the minus V set. So in the reverse bias configuration, the output of this diode will enter into the saturation region. Okay, so it will enter into the saturation region, and when it's coming into the positive cycle, or in the positive half cycle, so it will need some time to enter from negative half cycle to again its normal operating condition. Okay, so that's why there is a limitation of this precision rectifier, is that you cannot work with this precision rectifier for a very high frequency signals. Okay, so you can only work with a very low frequency signal. Suppose it's appreciable, or you may use up to some few ranges of kilohertz. Okay, but you cannot go beyond suppose 50 kilohertz, 20 kilohertz. Maybe it will work like within 1 or 2 kilohertz it will be able to work, but for higher frequency ranges this circuit will not work properly. Okay, so that's the limitation of these precision rectifier. But the major advantage of this type of precision rectifier is that it can work with a very low amount of signals. Okay, that is lower than the threshold voltage. So that's the majority issue, or that's the main major concern of this precision rectifier. And another major concern is the linearity operating region, because the op amp will only work in the linearity property. Okay, so due to this causes, precision rectifier is so much useful for rectification purpose. Then we will try to see the full wave rectifier. Full wave precision rectifier. Okay, so this is the full wave precision rectifier circuit. Okay, so right now we will try to formulate how the output voltages will looks like. Okay, so for the first positive half cycle, V in is greater than 0. Okay, so what will happen? So if we just consider like this way, that in the non-inverting terminal you are providing 0 volt, and in the inverting terminal you are providing the high signal value or a positive signal value. So from the output of the op amp we know that is V1 minus V2. So the output of this op amp will be negative value for this configuration, because this is the V2 and this is the V1 right now. Okay, so here you can say that V2 is connecting with the with some positive voltage right now. So you can say the output of this op-amp will be very high negative value. So if the output of this op-amp is very high negative, then what you are actually providing, you are providing negative voltage over here and you are providing negative voltage over here. So as a result, this diode D1, this will be in the conducting mode, this will be in the conducting mode, and this D2 diode will be in the reverse biased condition. Okay, so this will be the circuit configuration. These types of circuit configuration will become in the first half cycle. Okay, so right now, if we try to see that what will be the voltage of this particular circuit right now, if we try to see, okay, so if we utilize right now, if we utilize the virtual ground concept, okay, so in this particular configuration there will be 0 volt. Okay, fine. So what you can say that when this diode D1, it becomes in the forwarding concept or in the forwarding region, so there will be a feedback path. Okay, so when this diode is in the feedback or closed loop feedback path, then we can apply the virtual current concept. So that's why we have write down the 0 volt that has been appearing at also the at the inverting terminal. So if you look into for the second op-amp, second op-amp, so here you can see the non-inverting terminal of the second op-amp is connected with a resistance, and ultimately the resistance path is also connected with the 0 volt. So if we just try to redo the construction of this particular circuit diagram, you may or we may write or draw the circuit configuration like this R. Okay, now what will be the ultimate voltage drop in this particular node? So we know that in the op-amp, through the terminals there will be no source of current flowing, right? So in this particular node there is I is equals to 0. As I is equals to 0, so there will be no voltage drop in this resistance. Okay, so over here the output or the voltage that has been appearing into the non-inverting terminal of the second op-amp will be simply 0. So what will be the appearing voltage for the first op-amp over here? So right now this is simply a inverting voltage or inverting circuit. So here you know that is V0, it will become the minus input voltage into feedback resistance divided by the input resistance. So the output of this first op-amp will be simply V negative V in. Okay, so again this V01 will become the input signal for this particular portion. Okay, So what will be the output of this V out then? So the output of V out will be simply again minus V01 into feedback resistance R divided by the input resistance. So over here it's a minus V in, so R divided by R, so it will become V in. So whatever my input signal that will be directly at my output side. Okay, now for the negative half cycle, if we try to redo the circuit construction, so this is V in, so again this is R, 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 this is the V out. Okay, so right now if V in becomes less than 0, okay, so if it's becoming less than 0, so what will be the voltage appearing in this particular configuration? It will be definitely a very high positive value. Okay, so this diode, the upper diode, the D1 diode, this diode will be in the reverse bias mode, so this will not be in the working condition, but this diode will be in the forward biasing mode. Okay, fine. So what will be the output, or how we can find out the output voltage, right? Okay, so how we can find out the output voltage? Okay, so to find out the output voltage, so this is the value R. Okay, so first of all you have to find out that what is the op-amp's condition. Okay, so if we consider the second op-amp, okay, the second op-amp one, so this second op-amp is in the feedback condition or feedback connection, right? So there will be some voltage drop, or there will be some voltage at this particular point. Suppose this is V1. Okay, so as this second op-amp is in the feedback connection, okay, so it's, so again we will use the virtual voltage concept. So if V1 is appearing at the negative in terminal, so V1 will also appear at the positive terminal. So this is definitely V1 and this is definitely V1. Okay, fine. Then how or what will be the voltage for this first op-amp? So again this first op-amp is in the feedback connection, so we may use the virtual ground concept right now because the non-inverting terminal is connected with 0. So this is 0 and this will be 0. So in this particular node, how the actually current is flowing. So if you just go through like this, if current is flowing in this direction, so that's entering, then this current is leaving, then this current is also leaving. Suppose this is the I1 current, this is the I2 current, and this one is the I3 current. So if we try to formulate the values or use the KCL value right now, so the I1, it will be equals to I2 plus I3. So what's the value of I1 right now? I1 value will be V in by R. It will be equals to, what is the I2 value? I2 value is nothing but that is flowing through this branch. So it will be minus V1 divided by twice R, and I3 value will be simply minus plus 0 minus V1 divided by R. So if we do the calculation right now, so V in by R is equals to minus 3 by 2 R V1. So V in is equals to minus 3 by 2 V1. Okay, fine. Then for the next half, that means over here up to this much right now. Okay, now in the next half portion, you may say that current I2 is coming over here. Okay, then what should be the current that should flow through this op-amp? So because we have already known that for all op-amp there should not be any source of current flow that should flow inside the terminal. So there will be no current flow through the terminal. So there is I, it will be 0, and over here I will be also 0. So what the current is coming I2, the same current will leave over here, that is suppose I4. So I2 is equals to I4. So I2 is nothing but it's minus V1 divided by twice R, and I4 is V1 minus V0 divided by R. So minus V1 by 2 is equals to V1 V1 by, yes, it will be V1 by 2 is equals to V1 minus V0. So V0 will become V1 plus V1 by 2. So from this equation, V in is equals to minus 3 by 2 V1, and from here we have already formulated V1, V out is equals to 3 by 2 V1. So definitely V out will be equals to minus V1. So in the negative half cycle, your voltage is already in the negative part. So whatever you provide the negative value will ultimately give you the positive signals. Okay, so it's negative V in. So due to this equation, as my input signal is becoming negative, so the output of this signal will be also positive. So with this particular configuration, you may have both the two cycles in the positive half cycle. So that's the working principle for the full wave rectifiers as well for the half wave rectifiers. Okay, so that's the last part for the PMMC coil. Okay, so suppose if you are asked, you may see that whenever you are working with a very low amplitude signal, with a very low input signal, so definitely without looking for any other orientations or any other configuration, just simply go for the precision rectifier. Okay, so one catch is that the input signal must be lower than the threshold voltage signal of a diode. That's the first catch. Okay, now the second catch is that it will improve your linearity. Okay, and linearity property will only work when you are working beyond the threshold voltage level. Suppose that's your threshold voltage level is 0.7, so definitely you have provided a higher value than the 0.7 volt, and it's not the drawing current of the diode is not properly linear. Okay, so due to these two reasons, you must use the precision rectifiers. Okay, so precision rectifier is actually a more precise version or a more accurate version for getting using in the PMMC coils. Okay, so nothing is too difficult, because in this suppose when we are utilizing, so this will after this point you will just simply connect your, so like this way. So if this is the precision rectifier, the output, the V out, will be connected with RS, and it will be connected with a IM RM. So if this is your input signal, so like this manner it will be connected in this way. Okay, so depending upon the orientation of the precision rectifier, it will work in the full wave or it may work in the half wave. So it's your choice which one you want to choose right now. Then later this part I will we will try to see the electrodynamic meter. So what's the advantage of electrodynamic meter? Why we are using this sorts of meter? So up to now you have seen in the PMMC coil, in the PMMC what we are using a permanent magnet, and within the permanent magnet we are implementing a moving coil. When current is flowing through, the coil is moving in a particular rotation or in a particular direction, right? So that's the PMMC. But right now in the electromagnetic electrodynamic meter, what we will do, instead of one permanent magnet, we will try to use the fixed coils. So this is just a simple soft iron core. And this part Okay, so this is the orientation. This is called the fixed coil. This is called another fixed coil, and this one is called the moving coil. And with this moving coil, a pointer is connected. So a pointer is connected, and there will be the scales. Okay, so right now, if we just provide the positive and negative polarity like this way, so the current will be flowing in this direction. So the direction of this current will be in this way, and the orientation of the fixed coils, both the fixed coils, they will have the same orientation winding, but in the moving coil the orientation will be, the coil winding will be in a totally different direction. Okay, so in this configuration, current is going like this manner. So over here the direction of the current will be like this way. Then again current is leaving. So right now the direction will be like this manner, and current is leaving. Okay, now if we use Fleming's right hand rule, okay, so how we can say that if we use the Fleming's right hand rule, so definitely if this is the direction of B, sorry, this is the direction of I, over here B will be like this manner, and there will be north pole and there will be south pole. Okay, so right now in this fixed coil number 1, if we apply the Fleming's left hand rule, Fleming's right hand rule, so you may see that current is entering, the direction is upward. Okay, so there will be generation of north pole, there will be generation of south pole. So again for the fixed coil 2, so again the current is going upward, so there will be generation of north pole and there will be generation of south pole. Now what will happen for the moving coil? Okay, so in the moving coil the current direction is in the downward, so the direction, it will be over here, it will be N, and over here it will be S. Okay, so if we look closely into the polarity of these fields, so here you can see when the south pole is generated over here, the south pole will also generate over here. When north pole is generated over here, again the north pole will generate over here. Now we know the same polarity will oppose each other, right? So what will happen? This south pole will try to push the force into this direction, and this north pole will try to oppose this north pole into this direction. So what will be the ultimate movement of this pointer? So definitely as the moving coil is in moving in this direction, so the pointer will rotate in particular this direction. Okay, that's the first case. Now if we go for the second case, suppose there is plus, there is negative, so what will be the current direction? So right now there is the current direction like this manner. So let me change the color, actually it's not visible. So positive, negative. Okay, so it's in this direction. So right now current is entering like this manner. So current is going in this direction. So right now again, if we apply the Fleming's right hand rule, so this time over here north will be generated, and over here south will be generated, and in the moving coil south will be generated, north will be generated over here, and over here north will be generated and south will be generated over here. So again the same principle, and again the north pole will try to oppose the north pole, so this will try to oppose this, and this south will try to oppose this. So as a result, again the pressure or the force will be applied in this direction. Okay, so whatever the polarity or whatever the orientation or the voltage source, every time the deflection is in a particular direction, whether you provide these sorts of voltage arrangement or you provide these sorts of voltage arrangement, every time the deflection will be in the same direction. So that's the advantage of this electrodynamic meter. Because if you apply, you may use the AC signal as well as the DC signal input voltage sources in this electrodynamic meter. So that's the advantage. In the PMMC only DC is applicable, but for AC you have to provide the rectifiers. But in the electrodynamic meter you don't have to provide any sorts of what you can say, any sorts of rectification circuits. Okay, now there are some certain things that you need to know, because uh, again there is the same arrangement like the PMMC and the you can say the electrodynamic meter, they have the same sorts of arrangement, because whenever a deflection is being produced, so definitely you have to again make the pointer to its initial position, so you have to provide the hair springs as well in the electrodynamic meter. So let me just give you a circuit orient or physical construction. Okay, so before going into the controlling torque or the to get to know about the damping torque, so first of all what I will do, I will try to formulate the deflecting torque. Okay, so what's the deflecting torque? Deflecting torque, TD. So TD is nothing but it's the force into R. Okay, so right now what will be the force? The force will be definitely BIL. Okay, now if we look into the coil turn, so this is the length, that is L, and this is the total radius, that is 2R. Okay, from the axis point, if it is R, then the overall width will be 2R. Okay, then the current is flowing, that will be I2. Okay, so this is I2 we are gazing. Now what will be the effect of B? So we also know that B is proportional to the current. Okay, so what's the current? The current that is flowing through the fixed coil. Okay, so let us assume that the current that is flowing through fixed coil is I1, and the current that is flowing through the moving coil it's I2. So how we can say that B will be equal? Yes, so just let us use a simple constant value, that is K. Okay, so we know from the equation is that it will be B I2 L. Then what is the value of B? B is nothing but it's K I1 I2 L. There is R, there is also R. So this is only for a single conductor. Now if we go for the total conductor, so the total deflection will be nothing but it will be 2D. Okay, so 2K I1 I2 LR. So the total deflection or the total deflecting torque, total TD for n coils or n turns of coils, it will be simply n K I1 I2 L into 2R. Now L and 2R. Okay, so if this one is L and the total is 2R, then it will be the effective area A. Okay, and for this electrodynamic meter we can see the current that is flowing through the fixed coil, the same current is flowing through the moving coil. So we can say that I1 is also equals to I2. So the total deflecting torque TD will be equals to N K I2 square A. Okay, so if we consider the turns, the K and the A, all are constant value, so the deflecting torque will be proportional to the current that is flowing through the moving coil. Okay, so deflecting torque is directly proportional to the current that is flowing through. Okay, now for the simplicity purpose, okay, for the simplicity purpose in the PMMC we are saying that there are three opposing torques. One is the controlling torque, then we have the damping torque, then we have the inertia torque. Okay, now for the simplicity purpose we are just only considering the controlling torque. Okay, so over here what we have, TC is equals to TD, that is the TC is the controlling torque. So we know the controlling torque TC is equals to K theta. Okay, and theta is nothing but theta is the deflection. So if we just imply K theta is equals to NK I square A. So from here if we just remove all the constant values, so again we can say the deflection theta is also proportional to the current that is flowing through the moving coil, the square, that is proportional. Okay, so these are the two things that we need to know, that whatever the deflection is directly proportional to the value of the instantaneous, okay, square of the instantaneous values. Okay, so that's it. And the controlling torque is also provided by the hairspring. Now if we look into the construction of this electrodynamic coil, okay, so here you can see that right now, here you can see there is the spring coil for control action. Now to provide a damping effect, okay, so in the PMMC the damping effect is provided by the eddy current, but over here we are providing the mechanical damping. So how the mechanical damping is being provided to this meter? So to provide the mechanical damping, they have provided aluminum damping vane. Vane is nothing but it's a simple blade. Okay, you may just consider a simple blade that is connected with the pointer. Okay, so when the pointer will rotate, the vane will also rotate, and this vane and this part is the vane. So this vane is implemented inside a closed chamber. Okay, so here you can see that this is the cover, and this cover will help you to just create a closed chamber. Okay, so in the closed chamber, this is a yard tight closed chamber. So there will be definitely some air, but the air cannot come out, and also no air can also go into the chamber. Okay, so how this vane will provide you the damping effect, the mechanical damping effect, mechanical damping. So how this mechanical damping will be created? So when the pointer is moving, in this direction, the vane will also rotate in this direction. So when the vane is rotating in this particular direction, here you can see that the chamber is filled with air. Okay, so when the vane is rotating in this direction, there will be air force or air pressure in the opposite direction. Okay, so this opposing pressure will ultimately create you the damping effect. And again, when the pointer is coming to its initial condition or initial position, so at that time the vane will also rotate, or vane will move in this direction. So when the vane is moving from right to left or in the anti-clockwise direction, it's rotating in the anti-clockwise direction, then air pressure will be provided in this direction. So this is the air pressure, and also this is the air pressure. So again, so every time the air pressure will just play in the opposing factor in which direction the vane is moving. Okay, so this will ultimately provide you the mechanical damping. Okay, so one thing to add with this particular dynamic meter is that you have to use a calibrated scale. Okay, so why the calibrated scale? So you have already seen the theta is proportional to I square, the current that is flowing through the moving coil. Okay, so the I, it's nothing but it's the instantaneous value. Okay, so right now if I is equals to ip sine of omega t, so right now I square will be simply I square p sine omega t. Okay, so if we try to, if this is the signal, then definitely the I square value will be in the positive axis, right? So how you may find out the total integrated value? So you have just to do the integration. Okay, so if we do the integration of this particular signal, so what you will see, you will see that if we provide the integration, that is from up to 0 to pi, and the time frame is also pi, so I p square sine omega t dt sine square omega t dt, so this ultimate value will become something like this: I p square by 2 1 by pi into pi. If you do the whole integration, so ultimately the value will become this. So you may consider this ip square by 2. Okay, so the I square, integration of I square, so this ip square is nothing but it's the I RMS square. Okay, why RMS? Because I RMS is nothing but ip by root 2 whole square. So the theta deflection is actually the same of I RMS square. So that's why in the calibrated scale you have to provide the RMS values. Okay, that's for AC. And if you do the DC, so what's the RMS value of any DC value? The RMS of any DC value is the DC value itself. Okay, so suppose if you provide how you can say that just you have a 2, so definitely what you have to do, you have to square then the root. Okay, so what you do, so in this particular formation, so root mean square, suppose you have a 2, then you are providing the root, then you are again doing the squaring in configuration. So DC value, the RMS square value will just provide you the DC value itself. So you have to do the calibration while maintaining or making the scale, so that the RMS value and the DC value can be shown in a single scale. Okay, so that's the calibration, that's why calibration is needed. Now another thing is that what's the feature of this particular dynamic meter? The biggest feature is that you may use the AC signal and the DC signal at the same time. You don't have to use any sorts of rectification circuits. But the major disadvantage is that it's totally conductive, or a coil mechanism. So if you provide a very high input signal or very high current, so definitely the temperature will increase of this coil, the fixed coil and the moving coil, so definitely the resistance will vary. Okay, so that's why the disadvantage of this particular meter is that there is a limiting factor of providing the current or providing the input signals. So that's it, and we have come to the last part of our syllabus, that is the electronic AC sorry, it's electronic analog DC voltmeter. Now so if you look into the particular figure here, you can see that we are utilizing the PMMC movement. Then there is a multiplier resistor. Then there is amplifier, input switching, and range selection. So for a multi-range DC voltmeter, for a multi-range analog DC voltmeter, so what we are doing, we are using some sorts of mechanical switches, okay, to select the ranges, okay. But right now, instead of utilizing some mechanical switches, we will try to utilize the electronic switches. So definitely switching purpose, whenever we are utilizing the switching, so definitely it's MOSFET or BJT, okay. So MOSFET is much more faster, so that's why we are using the MOSFET for switching purpose. And amplification, so there is a certain reason why we are providing the amplification. So if you look into the figure, the upper portion and the lower portion, that is that here you can see A and B. After A and B, okay, so after A and B, multiplier resistor and PMC mechanism is added. So with this multiplier resistor, what you will do, you will just provide the resting operation, that is my over here there will be RS, then over here there will be the RM or the PMMC, okay. So that's it, that's the multiplier resistor, nothing but it's the RS value, okay, and PMMC is the rest mechanisms, okay. And whatever before AB, okay, so this total part is nothing but it's the input switching block and the range selection, and as well as the amplifier block, okay. So in this particular section, this portion up to this much, this portion is related with the input switching and range selection, and the next portion this portion is replaced by this amplifier block. Now for multiplier resistor, how actually or how this electronic device is actually working. So suppose you want to select different ranges, okay, 10 millivolt, then 100 millivolt, then 1 volt, then 10 volts. Suppose these are the ranges, okay. So you want to select these ranges, these 4 ranges you want to select, okay. So but every time you cannot provide higher voltages, okay. So in this particular configuration, it has been configured or oriented in such a way that this circuit will operate and lower than or at 1 volt, up to 1 volt. This circuit will work up to 1 volt, okay. So you cannot provide beyond 1 volt, okay. So up to this point or at this point, you have to provide 1 volt. So whatever you select the range, okay, so 10 millivolt. So if your input signal is 10 millivolt, so at the output side, maximum that is going to operate, that is the 1 volt. So over here you have to create a 1 volt signal at the output of this amplifier. Okay, so there are some certain things that you need to maintain, that while doing or making some different ranges voltmeters. Okay, so the thing is that at the output side, here you can see at this output side of this amplifier stage, in total you have in total 100 kilo ohm resistance. Okay, this should be fixed. You cannot increase your voltage ranges, resistance values beyond the total summation should be within the summation of the all the resistance at the output side. It must be 100 kilo ohm. It must not cross 100 kilo ohm. Okay, or it must not lower than 100 kilo ohm, exactly 100 kilo ohm. How many stages of gain you want to select? Okay, so the summation will be definitely 100 kilo ohms. Okay, so this is at the output side of this circuit, it should be 100 kilo ohms, and at the input side this portion should be also fixed, these portions. Okay, so the voltage ranges should be fixed, it should not vary. Now the main thing is that the switching, how the switching will be done. Okay, so it's connected in a way that S1 and S3 is connected, then S2 and S4 is connected. Now when S1 and S3 will be activated, so S1 and S3 will be activated when the input voltage range is lower than 1 volt, and when your input voltage range is higher than 1 volt, okay, or equal to 1 volt, then S2 and S4 will be activated at that time. Okay, now this is the thing. Okay, so S1 and S3 is connected together, and S2 and S4 is connected together. Now depending upon the gain, the S3, S5, S6, S7, these three switches will be activated depending upon the gains. Okay, so how much gain you want, so in this way it will be selected. Now for the first scenario, that is the 10 millivolt scale. Okay, now for the first case, when my input signal is 10 millivolt, so it's definitely lower than 1 volt. So at that time S1 and S3 will be closed. Now I know that the AB terminal. Okay, at the AB terminal I have to generate 1 volt. Okay, so when 10 millivolt is applied in this way, so this S1 will be shorted and S3 will be shorted also. Okay, so right now over here 10 millivolt will be appeared. So when 10 millivolt is appearing, right, so I know that through the input terminal, as right now through this resistance no current should be flowing, because that is at the input terminal no current, the current should be 0. As no current is flowing, so the voltage drop across R1 will be definitely 0. So whatever you apply, your applied voltage will directly appear at the non-inverting terminal. Okay, so at the non-inverting terminal 10 millivolt is appeared. Okay, now this 10 millivolt needs to be converted into 1 volt, right? So which gain factor it should be selected? Okay, so V out will be, what will be the V out? V out will be definitely, so in this particular configuration, so 10 millivolt, to generate from 10 millivolt you want to generate a 1 volt. Here you can see the S5 will create a gain of 1. So if S5 is activated, so what you get at the output, you will definitely get 10 millivolt, but you don't want 10 millivolt, you want 1 volt. Okay, so if you go for the 10 times multiplication S6, then you will get a 0.1 volt. So again it's not required. So you have to create a 100 gain factor. So to create the 100 gain factor, what you have to do, the S7 will be shorted. When the S7 will be shorted, at that time all these S3, S5 and S6, they will be kept open. So what will be the circuit diagram at the time? Suppose this is the V in, then over here it will look like something like this. So at this time there is 90 kilo ohm, and over here, sorry, you will have 99 kilo ohm, and over here you will have 1 kilo ohm. So if you look over here, that when S7 is being shorted, so these two resistance, 90 kilo ohm and 9 kilo ohm, they are in the series configuration. So it will be 99 kilo ohm and the remaining will be 1 kilo ohm. So if we just utilize the formula for the non-inverting amplifier, that will be V out will be V in 1 plus RF by R input impedance or input resistance. So V in is 10 millivolt and over 1 plus 99 by 1. So you will be able to create a 100 gain factor. Okay, so it will be 1 volt. Now if you select 100 millivolt, if you select a 100 millivolt, now how we can create 1 volt? So definitely we have to need to select the 10 gain factor. So only at that time S6 for 100 volt. Okay, if you provide 100 millivolt, so if you provide 100 millivolt, then S1 will be shorted, S3 will be shorted, and you need a 10 gain factor, so S6 will be shorted and all the other things will be kept open. So as S6 is shorted, so R4 becomes the feedback resistance, and 90 and 1 kilo 10 kilo ohms becomes my input resistance. Okay, so for the second case, if it's 100 volts, so V out is equals to V in 1 plus RF by R1. So over here 100 millivolt into 1 plus 90 by 10. So finally you will be able to get a 10 gain factor. Okay, so the next configuration, if we select a 1 volt scale, okay, so if we select a 1 volt, so as I have already mentioned that what is the system, or what's the principle, that how is going to work. S1 and S3, they are shorted together, and S2 and S4 is shorted together. So S1 and S3 will only activated when the voltage range is lower than 1 volt, and S2 and S4 will be activated when the voltage range is higher than 1 volt. Only at that time it will be activated. Okay, so for this particular configuration, so when we are working with 1 volt, so that is definitely not lower than 1 volt, that's exactly 1 volt, or you may say it will be only applicable for 1 volt and higher than 1 volt. So for this case, for the third case, when we are my input voltage range is 1 volt, at that case S2 and S4 will be shorted. So it will be shorted, then S4 will be shorted. So if my input signal is 1 volt, then whatever the voltage is appearing over here, that V input, this V1 signal, it needs to be amplified with some gain factor. So what will be the V1 in this particular scenario? So V1 will be nothing but it will be R3 divided by R2 plus R3 into V in. So for the time being, R3 is 100 kilo ohm, and R2 plus R3, they are 9.9 mega plus 100 kilo ohm into 1 volt. So if we do the calculation for the first numerator and denominator portion, you will be able to get by a fraction, that is 1 by 100 into 1 volt. So what will be the value? The value will be definitely 0.01 volt. Okay, so 0.1 volt, 0.01 volt is appearing over here. So again, from 0.01 volt, what you have to do, you have to create, or you have to amplify this 0.01 volt to 1 volt. So definitely we have to select this 100 gain factor. Okay, so S7 will be shorted. Okay, so again this will become the RF and this will become the RI. Okay, now for the last scenario, if I am selecting a 10 volt scale, okay, if I am selecting a 10 volt scale, then at that time what will be the V1 value? So if R3 divided by R2 plus R3 into V in, so if R3 is 100 kilo, R2 is 9.9 mega plus 100 kilo into 10 volt, and it's about 100 into 10, so that will definitely give 0.1 volt. So from 0.1 volt you have to select, you have to go 1 volt, so there will be an amplification factor of 10. Okay, so at that time the output V out will be V in 1 plus RF by RI. So V in is what, 0.1 right now, because not V in, actually it should be V1 into 1 plus 90 divided by 10. So ultimately you will be able to get 1 volt. Okay, again if we just select again for 100 volt, if this is the scale, then what will be the scenario? So if it becomes the input voltage becomes 100 volt, then you will get definitely 1 volt. So you don't need any sorts of amplification factor, right? Because right now in this scale, in this case you are gaining, suppose you are selecting 100 volt. Okay, so over here you are getting 1 volt, so you don't need any source of amplification factor. So what you need to do, you just need to use the buffer circuit arrangement. Okay, so what you do, you just have to short this S5, so it will be in the buffer orientation, as there is no uh, feedback resistance, so it will be 0. So whatever your input signal 1 volt, that will be appeared at the AB terminal. So 100 volt will be stepped down to 1 volt and it will be able to tolerate by the PMMC. Now the last portion is that if you are being asked to create a range, suppose or you are being asked to design in the multimeter or this DC voltmeter analog part amplification factor, you have to design for different ranges. Suppose over here they have it's showing like 10 millivolt, then 100 millivolt, then 1 volt, 10 volt, then 100 volt. These are the orientations. Okay, now instead of this, suppose 10 millivolt is there, then 100 millivolt is there, then there is suppose 20 volt is there, 50 volt is there, then you have a 100 volt arrangement. Okay, so if we go for these arrangements, okay, then how it will be working? So right now we are selecting 20 volt, so 20 volt is definitely higher than 1 volt. So what are the switches that you need to connect for 20 volt? for 20 volt. Suppose it's 20 volt right now. So these two switches will be shorted. Okay, so what will be the voltage that will appear over here? V1. So V1 will be equals to the voltage drop R3 divided by R2 plus R3 into 20. So R3, it will be definitely the ratio I know, that is 100 into 20, so 0.2 volt. So right now there is a voltage of 0.2 volt. So from 0.2 volt you have to go to 1 volt. So what should be the amplification factor? The amplification factor should be 5 right now. Okay, so how the amplification factor should be created? So I am just only considering the amplification factor. So if it will be 1 plus RF by RI, so it's 4 is equals to RF plus RI. So whatever the input resistance, that should be the 4 times for the feedback resistance. Okay, so but you have to maintain a ratio. Okay, you have to maintain the ratio for, or you have to maintain the total summation of what you can say 100 kilo ohms. Okay, so what you can do, if you just say suppose 10, if R1 is 10, then what you can just configure in this manner, suppose if I select Ri is 20 kilo ohms, then Rf is what? Rf is 80 kilo ohms. Okay, now how you can actually create this variation? So in this 90 kilo ohms, okay, in this 90 kilo ohms, instead of using a single 90 kilo ohm, what you can do, you can use two separate values. Okay, so over here you may use a resistance and another resistance. So the first resistance should be 80 kilo ohm, the second resistance should be 10 kilo ohm, and the remaining will be 9 plus 1, another 10 kilo ohms. Okay, now in between there will be another switch which will be give you a gain factor of 5. So if I look or if I just try to rebuild the circuit, then it will looks like something like this. These are the parts, they are the same. So this is the first part where its gain factor is 1, then there is a gain factor of 5. So over here there will be 80 kilo ohm, then 10 kilo ohm. This is the gain factor for 10. Then we have 9, which will ultimately give you the gain factor of 100, and there is the last one, that is 1 kilo ohm. And they are the switches. They are the switches just. Okay, the switches, suppose this is S3, S5, S6, S7. Okay, they are the switches. Now for 50 ohms, for 50 volt, if your input signal is 50 volt, then what you will get over here, R3 by R2 plus R3 into 50. So this ratio is nothing but it's 1 by 100. So you will get a 0.5 volt. So what should be the you can say that gain factor? It should be 2. Okay, so it should be 2. The gain factor should be 2. So 2 is equals to 1 plus Rf by Ri. So it will be definitely Rf is equals to Ri. So what you can do, you may just provide 50 ohms. Rf and Ri both should be 50 kilo ohms. So what you can do, instead of right now, instead of this 80 kilo ohm, you may distribute these 80 kilo ohms into 50 and 30. And this is gain factor 2, this is gain factor 1. This is the switch, and over here you have 50 kilo ohms, then over here you have 30 kilo ohms. Okay, so if you do the whole calculation, then and when this gain factor is activated, so at that time all the other switches will be turned off. So if Rf becomes 50 and you do the whole summation for this part, then it will also become 50. So as a result, you will be able to get a gain factor of 2. So that's it for your last lecture. I know it will be a little bit lengthy, so try to understand all the concepts slowly, because it's a very long video lecture. So if you right now, if you face that you are not able to understand that particular topic right now, so go through that topic again. So to review that particular portion, and still now if you don't understand, or if you feel any sorts of confusion in that particular section, just let me know, then I will try to review those sections in the classes again. Okay, so that's it for your final syllabus for the measurement and instrumentation course. So a very huge course. So I tried my best to convey the all things to you, but it might happen that I may have done some mistakes in all over the semester. So try to pardon or forgive those mistakes, and let me know if you think that if any a particular portion I have done a mistake or not, so that I can rectify myself. Okay, so that's it for the last lecture. Thank you. Assalamu alaikum everyone.